Hello, everyone. Today I'm presenting my final project, building a job resume recommendation system by engineering a signal where none exists. The core problem I tackled is one that every modern recruiting platform faces, which is matching. Whether you're LinkedIn, Indeed, or a university career center, the goal is always the same. We want to match candidates, our users, to job postings in a way that feels personalized and relevant. However, building a recommender for the job market is significantly harder than for Netflix. The stakes are higher. A bad movie recommendation costs you 2 hours of time, but a bad job recommendation can derail someone's career. Furthermore, the data is messy and unstructured. Today, I'm going to walk you through how I built a system that bridges this gap between unstructured resumes and aspirational job descriptions, specifically focusing on how to do it when you don't have access to proprietary user data. So let's define the task formally. I'm formulating this as a personalized ranking problem. The input is a specific user profile or resume, and the output is a ranked list of job postings sorted by relevance to that user. So why ranking and not classification? In the real world, a user might be qualified for 1,000 jobs, and classification just tells us, yes, they are qualified. That's not really helpful. Ranking tells us these are the best 10 jobs for you. This dictates my evaluation strategy. I am focusing on NDCG, which is normalized discounted cumulative gain. This metric rewards the model heavily for placing relevant items at the very top of the list, mimicking real user behavior where people rarely scroll past page one. So here's the major roadblock. Technically, recommender systems rely on explicit or implicit feedback. But in the employment domain, that data is proprietary. I don't have a database of who applied to what job, and this leads to the core challenge. How do we build a collaborative filtering system without any interaction data? It's kind of like a catch-22, where content-based filtering often fails because it misses semantic meaning, and collaborative filtering is impossible because our interaction matrix is empty. So I needed to engineer a solution. To solve this, I had to stitch together three distinct data sets to create a training pipeline. The first was a resume data set, which contained about 962 categorized resumes, and these represent our users. The next was a LinkedIn job postings data set, which was a massive file that contained millions of rows, but for this project, I sampled it down to only 50,000 rows to manage the sparsity of the matrix and also to not let it crash. And these are our items. The NER, or named entity recognition dataset, is the third one, and this acts as my Rosetta Stone of sorts. It contains pre-mapped skills that help me translate raw text into structured entities like Python or project management. So let's look at the distribution of our users. We can see that there is a heavy skew towards technical roles like Java developers, testing, DevOps, Python developers, web design. So while class imbalance is usually a problem in machine learning, in this specific project, it's actually helpful because technical roles are extremely keyword driven. For example, if you're a Java developer, you almost certainly have the word Java in your resume. If this data set were for sales or general management, extracting hard skills would be much harder because the language is more subjective and soft skill heavy. This distribution confirms that a skill-based extraction approach is viable for this specific population. So these word clouds illustrate why simple text matching fails. I generated these word clouds for both data sets. So on the left is the resumes in the blue. You can see words like experience, project, months, company. These are past tense descriptive words. A candidate is describing what they did, while on the right in the red are the jobs, and you can see team, business, clients, role. These are aspirational future tense words. A company is describing things that you may do in the future. So because these two documents speak different languages, a standard TF-IDF model often is going to miss that connection. So we need a bridge, and that bridge is skill extraction. So my solution was to engineer an implicit feedback signal. I am operating under the assumption that skill similarity implies user interest. Here is the logic I applied. I extract a skill vector for every resume and every job. I calculate the Jaccard similarity between them. If a resume and a job share a statistically significant number of unique skills, I treat that as a positive interaction, or 1. If they do not, I treat it as a non-interaction, or 0. And this was the kind of aha moment. By generating these synthetic ones, I effectively converted a content-based problem into a collaborative filtering problem, allowing me to use powerful algorithms like matrix factorization. So how do we define significant similarity? So I didn't want to just guess, so I plotted their distributions. If we look at the histogram, the vast majority of resume job pairs have a similarity of 0. This makes sense because a chef's resume has 0 overlap with a data science job. But looking at the long tail on the right, these are the matches. I selected a threshold of 0.15. So any pair to the right of this line gets a 1 in the matrix. Any pair to the left gets a 0. And this threshold is critical. If I set it too low, the model learns noise, but if I set it too high, the matrix becomes too sparse to learn anything. So with my matrix built, I implemented 4 distinct model architectures to see which one would work the best. So the first one was a popularity baseline, which is the dumb baseline. It just basically recommends jobs that have skills everyone has, like communication or office. The second one is a TF-IDF recommender, which is a pure content model. So it ignores my engineered skills and it just looks at the raw text. So this is good for a cold start problem, but it lacks semantic depth. The third is an SVD or matrix factorization. And this is a classic collaborative filtering approach. It decomposes the interaction matrix to find latent patterns, like learning that pandas and NumPy are related. The fourth one is the hybrid model, and this is my proposed solution. It takes a weighted average skill of vector similarity and TF-IDF text similarity, so precision and coverage. And here are the actual final results of using NDCG. So we can see that SVD performed at 0.38. It performed the worst, which confirms that SVD struggles with the cold start problem. In my test set, the users were new, so SVD had no history to rely on. For the popularity model, it landed at a 0.73, which is surprisingly kind of strong. In tech, full stack jobs act as universal donors, so they match almost everyone. So they're going to have a lot of keywords that people are going to have matches to. For the hybrid model, it scored at a 0.99, which was the clear winner. It outperformed everything else by combining the structural rigidity of skill matching with the fuzzy flexibility of text matching. So first, I do want to be honest about this 0.99 score because, that seems suspiciously high. So there is a circular logic in my evaluation. I created the ground truth using skill similarity, and my hybrid model uses skill similarity as a primary feature. So to some degree, the model learned exactly what I told it to learn. It didn't predict user behavior, it predicted skill overlap. However, this is still a valuable result. It proves that we can successfully engineer a clean, learnable signal from unstructured text, which is the first step in bootstrapping a recommender system. So this work builds on three foundational papers in the field. This first one, Hugh et al. This seminal paper on implicit feedback, I adapted their concept of confidence in ratings to my concept of skill overlap confidence. This second one, Light FM. So my hybrid architecture is effectively a custom implementation of the Light FM approach, combining metadata with collaborative filtering. And then for this one, YouTube recommendations, while they use deep learning, my approach mirrors their two-tower concept of matching query vectors to item vectors in a shared space. To wrap up the slide deck, um, implicit feedback engineering is a viable strategy for the cold start phase of the product. If you launch a job board tomorrow with zero user data, this approach allows you to provide relevant recommendations on day one. Um, for future possible directions, if I were to take this into production, I would make two possible changes. So the first would be replacing TF-IDF with transformers to capture context. So understanding that looking for a manager and management experience are related. And another change I would make is A/B testing. So offline, a lot of these metrics, offline metrics are just proxies. The only way to validate my like truly validate the 0.15 threshold that I built out is to deploy this live and measure actual application rates. So this would be something that would need to be tuned over time with real data. Okay, so now I will do a quick walkthrough of my workbook. Okay, so now that we've covered the concepts, we can walk through the actual Python implementation. So here is where I loaded the three data sets that I mentioned in slide 4. You can see the code here where I downsampled the LinkedIn data set to 50,000 rows. Sorry here. This was necessary to keep the sparsity of the matrix manageable for the SVD calculations later. Um, section 3 here. So for the data preprocessing, here is a clean text function that I added. I want to highlight this specific regex line, resub. As I mentioned in the presentation, technical skills are sensitive to cleaning. If I had used a standard NLP cleaner, C++ would have become C, losing its meaning. So this custom regex ensures that we strip noise while preserving those critical characters like the plus plus in C++ or .NET or the dot. Um, okay, so section 4, feature engineering. I want to highlight this extract skills function right here. So this iterates through every resume and job description, comparing tokens against the NER vocabulary we loaded earlier. And if we scroll down, this, so this skills to vector, this block here is crucial. So this skills to vector function takes those raw lists of strings and converts them into one hot encoded vectors. This is the mathematical foundation that allows us to calculate the Jaccard similarity. Um, so if I go back up to the similarity distribution section, so here is the code corresponding to slides 7 and 8, where you can see the loop where I calculate Jaccard similarity for the pairs. And right here is where I set the threshold to 0.15. This line of code is what generates the binary interactions matrix, which is the synthetic ground truth that powers the rest of the project. And then for models, these are the four actual models that I built out. So the first one is the popularity, which is the simple summation of the interaction matrix. The second one, TF-IDF, which uses the TF-IDF vectorizer from scikit-learn. My model 3 is the SVD, and here I used the SVDS function. This performs the matrix factorization on the sparse interaction matrix we created. And then the fourth model is the hybrid. This class hybrid recommender implements the weighted average logic I described in slide 9. And you can see the alpha parameter here set to 0.6. And then finally, the evaluation loop. I implemented a user-centric split here. I didn't just split random rows, I held out entire users. So this code block calculates the NDCG, precision, and MAP scores that populated the bar charts in slide 10. Running this cell produces the final output. Um, and from the run that I had done, the hybrid model achieved the highest scores at 0.99, which confirmed the hypothesis that skill-based filtering is the strongest signal that we have available. This concludes my walkthrough. Thank you for listening to my project.